Hello, welcome to this class about the matrix of change of bases, which is the same as the matrix of change of coordinates but in the opposite direction. This is what we are going to learn. Let's introduce the notation. Here we have a vector space of dimension n, and for every vector in this vector space we will use this notation to express the coordinates of the vector with respect to the base b that we write here in the subscript. These coordinates will be understood as a vertical vector in Rn. And we will be working with two bases, b1 and b2. Here we have both. It's clear that for every vector in this vector space, you can express it as a linear combination of the elements in, for example, base 1. And I want you to understand, think of it carefully, that this linear combination can be expressed in this way. So the base, that is a horizontal vector, a vector of vectors, but certainly a horizontal vector, times the coordinates, which is a vertical vector of scalars. And we can simplify this in this way. So from now on, we will say that every vector in the vector space is the base times its coordinates with respect to that base. At this point, I want to clarify that these coordinates are unique. There is a result that guarantees this. What do I mean with unique? Essentially, unique means that if you find something, let's call it C, such that multiplying the base produces the vector, then this something C, must be the coordinates of the vector with respect to the base. This being said, it's clear that we can generate every element in the second base with linear combinations of elements in the first base. That's to say, this W, which is the first element of the second basis, can be generated as a linear combination of the elements of the first basis. And you can repeat the same idea with W2, W3, and so on. So at the end, we have that the second basis is just a matrix, what we call matrix of coefficients, matrix of scalars, times the first basis. If you take a look to this system of linear equations, you will understand that you can express this system in this way. All this horizontal vector equals all this horizontal vector times this matrix. When I call this horizontal vector, well, this is a vector of vectors. This is a matrix of dimension 1 by n, or even in simpler terms, we can say that we have proven right now that there exists a matrix of size n by n with entries in the real numbers such that the second base equals the first base times this matrix. Okay, so this matrix that we are talking about here, this one that we call P, you can see it here, and it's the same as this one here, is precisely what we call, or what I am calling now, P, the matrix of change of bases from B1 to B2. I call it the matrix because there is only one. In the same way that the coordinates are unique, as we saw before here in green, well, with more reason, this matrix is unique because at the end it's the matrix of coordinates of the second base with respect to the first. Let's talk now about some properties of P. It's easy to prove that this P is to the matrix of change of coordinates from B2 to B1. So notice that the matrix that changes the base is the same matrix that changes the coordinates, but in the opposite direction. So if the matrix changes from B1 to B2, this matrix changes the coordinates from B2 to B1. So the coordinates with respect to the old basis equal the coordinates with respect to the new basis multiplied from the left by P. Well, that's another interesting difference. When you change the base, the P multiplies from the right. When you change the coordinates, the P multiplies from the left. Now, let's prove that this is true. It's going to be very easy. If you have any vector, by definition, this vector is going to be the second base times its coordinates with respect to the second base. Now, the good thing is that instead of writing basis 2, we can write basis 1 times P. So what we can write here is basis 1 times P instead of basis 2. And now we apply the result that we got in green here. The idea is that this is playing the role of C, so certainly this implies that the coordinates of the vector with respect to basis 1 must be P times this, because the coordinates are unique. So anything that works as the coordinates must be the coordinates. In a similar way, we can work with the inverse of P, and we can say about the inverse of P that it is the matrix of change of basis from B2 to B1. Well, this is kind of obvious. It's so easy to prove this. Obviously, if B2 equals B1 times P, multiplying both sides times P minus 1, we get that B2 times P minus 1 equals B1. In a similar way, P minus 1 is to the matrix of change of coordinates from B1 to B2. And these are the three results that you must be aware of and you must be familiar with, because they are the ones that we use all the time. All this explanation was for any vector space of finite dimension. Now, let's work more precisely with the vector space being Rn. When the vector space is Rn, there is a simple way of getting the P. And this way is explained here. P minus 1 can be obtained performing elementary operations to convert. So you write here the old base, and you write here the new one. And you operate rows conveniently until you get here the identity. And when you get here the identity, you can bet that what appears in the right is the P minus 1. Why does this method work? Well, it's easy. It's because when you put these two matrices together, what you are guaranteeing is that whatever you do in the left, you do exactly the same in the right. So the question is, look at here. If in the left we had B2 and we ended up with I, with the identity, what did we do? There is only one answer. It's clear that what we did was multiplying by the inverse of B2. And since we operated with both things at the same time, B1 and B2, this operation that we performed in B2, we had to perform it as well in B1. In other words, we have the guarantee that we multiplied B2 minus 1 times 1. And if you do this, you will see that what you get is P minus 1. Why? Because B2 can be replaced, by definition of P, with B1 times P. So we can write this here. And now, applying basic algebra of matrices, you get that this is going to be P minus 1. In a similar way, we can get P performing elementary operations to convert this into this. So it's exactly the same. So the conclusion of all this is that the matrix that changes bases from B1 to B2 changes coordinates too, but in reverse. It changes coordinates from B2 to B1. And if you want to move always in the same direction, let's say from 1 to 2, then you need to get the inverse matrix. Because if you want to move always from 1 to 2, you will have to use this P for bases and the inverse of this P for coordinates. Because it is the inverse of P what will change from the coordinates with respect to B1 to the coordinates with respect to B2. Be aware that in some books they change the notation. In some books they call this the P minus 1 and they call this the P. The reason why they do this is because they start explaining all this for the change of coordinates. And once they have explained the change of coordinates, they explain that this matrix that changes the coordinates, when done inverse, it changes the base. I don't like this order. I don't think it's very logical because the concept of coordinates requires the concept of base. So I always think that it is better to explain it for the base and then to expand it to the coordinates. Another thing that I consider confusing is that many authors don't discuss the relations between the matrix of change of bases and the matrix of change of coordinates. For example, the book that we are using speaks about the transition matrix from basis 1 to basis 2. And this book defines this transition matrix in the way in which I am defining here P minus 1. That's to say, as the matrix of change of coordinates. To make this more confusing, they write this explanation about the matrix of change of coordinates under the title of matrix of change of bases. So you read matrix of change of bases, and indeed you never see the explanation about changing the base. You see mostly the explanation about changing the coordinates. So it's understandable that you may think that there are pieces missing. That's what I thought. Well, I trust that with this explanation you have all the pieces in front of you. The only thing that you need to know, especially regarding this book, is that the transition matrix is essentially the matrix of change of coordinates, which you can obtain with this simple procedure.